Okay, good afternoon, everybody. Let me just, I'll introduce the panel. My name is William McDonnell. I am COO of the Integrity Council for the Voluntary Carbon Market, the new global governance body setting standards for carbon credits, launched from the City of London. But I used to be CRO of RSA Insurance. I led a big study into climate change by the global insurers. But I'm a lay person when it comes to quantum. Let me introduce my panelists. So maybe I'll start at the far end. Dr. Sonali Mohapatra from the National Quantum Computing Centre. She's been leading the innovation sector and supporting their strategy and sectoral engagement framework, and particularly focusing on use cases. And she has a PhD in quantum gravity and foundations. Then, if I can move on to Dr. Carmen Palacios Beraquero, I hope I've got that right, who has a master's in physics from Imperial and a PhD from Cambridge in quantum computing, where she continued as a postdoc researcher and also in 2018 became founder and CEO of New Quantum. Then we have Matt Martin. Matt has been at Oxford Instruments Nanoscience for over 5 years, Senior Director of Engineering, and most recently Managing Director. He's a mechanical engineer with over 30 years of industrial experience, a lot of that in the semiconductor sector. Then finally, if I could introduce Mike Short, who was Chief Scientific Advisor at the Department for International Trade for over 5 years, is that right?
5 1/4.
That quarter counts. And has over 40 years of experience in electronics and telecoms, particularly VP at Telefonica for 17 years. And now I believe also you are working in the space sector, and you were also awarded a CBE back in 2012 for services to the mobile industry. So, quantum for good. The first question I want to start with is, so fundamentally, the climate crisis is about chemicals, CO2, methane, and various others. What I wanted to do first, actually, is to ask Carmen, how can quantum help tackle climate change problems, and what is it best suited for?
Sure, thanks. So first of all, I must say that New Quantum, the company that I lead, is one step removed, actually, from end-use cases. We build hardware to scale quantum computers to the kind of sizes that are needed to tackle some of these problems, but I can act as a bit of a translator. So why quantum computers are good, they will help and have a huge impact in the climate crisis, is because some of the key problems that we already know will have a huge impact are chemistry and material science problems. And so today, supercomputers can't simulate these materials, these molecules. They're quantum mechanical objects, and we don't know how to accurately simulate them without quantum computers. Quantum computers, that's what they do. What they do best is to simulate quantum objects. Current supercomputers work on approximations, and so currently the process of designing a new molecule or implementing a new chemical process relies on many years of repeating lab experiments and trial and error kind of development. So the reason I like this use case is because we already understand the processes where we just need a particular molecule or a catalyst or adsorbent to really, really make a huge difference. And we know more or less what it would have to look like, but we can't accurately simulate it. We need a quantum computer for that. So we can discuss in more depth specific applications, but things like absorbents or solvents for carbon capture, the more accurate design of batteries for different use cases, things like the processes to make fertilizers. These are processes that are in place, that we understand very well, and where we could identify where quantum computing could help. But these applications are the kind of longer-term applications of quantum computing. So we do need what we call fault-tolerant quantum computers. So no jargon, really big, million-qubit quantum computers. So I'll leave it at that.
Well, Matt, if I can just turn to you and building on that. So why is quantum a good fit for these challenges, and how useful can it really be to tackle them?
I think any tool that we have, and I'll use the term of quantum computing as a tool, that actually enables a more efficient development of a process or the development of a design or the solution to a problem can only be a good thing. Ultimately, one of the things that we do at the present time is we spend an awful lot of resources solving things, consuming things, and developing things on the planet. Now, I'm quite a simple person, and I like to sort of use analogies. And my background, as mentioned, is semiconductors. So I spent a lot of years both developing the tools that make silicon chips, but then I spent a bunch of time doing the bucket and spade chemistry of abatement, tidying up all the pollution that came from the processes of manufacturing silicon chips. Now, to the point that Kalman's making, a lot of that is chemistry. And a lot of those chemistry problems, we understood enough about them to make use of them to actually do something generally useful. And everybody's got a bit of silicon or gallium arsenide or gallium nitride in their pocket today, so we can claim some use there. However, in a lot of those processes, we ended up perhaps using more material, more energy, more everything than we actually needed to get to the outcome that we wanted, purely and simply because we didn't actually understand fundamentally the preciseness and the optimization of the chemistry. So imagine if you could do that and how much more efficient the process would be. Once you've got an efficient process, of course, the stipulation is, well, it's great, I've now got a new tool. As a global population, what do we do with new tools? Well, the answer is we use them more. So we've gone from a possible position where we have optimized and we've made better energy use in order to create an outcome, and then we've used it 10 times as much and perhaps undone a lot of the good work that we have done. However, there is investment to be done along the way. So the reason I'm really interested in quantum is because if you can make better tools, and actually if you know that in making better tools, you're going to deploy better solutions, and if you can see those solutions coming and you know that the way to optimize them early, because you know they're coming, is to actually invest in the bits of technology that you need to do to make them more energy efficient, environmentally useful, then quantum ultimately is a really good opportunity to rebuild a lot of what we do today for better outcomes and ultimately being more efficient. So that's what excites me potentially about the chemistry part of quantum.
Okay, great. And actually, if we move from the chemistry side, Mike, you have had a career in the telecom sector, and as I say, a chief scientific advisor, and now looking at space. So how can the space sector help to address the climate emergency, and can quantum be a game changer, and if so, how?
So a couple of examples of what we're doing today as the Satellite Applications Catapult, and then come to quantum technologies, if I may, to your question. One example is we're already working with a Canadian company called GHGSat, looking at methane emissions, and we can observe them from space. But the only way we could do that is to gather the data with the satellite observation from above, and then put in clever processing with clever academics, and lo and behold, we can detect methane, which is worsening our planet. What we need quantum for is to help speed up that process to make sure that we can accurately detect and sense some of these pollutants in the environment. Clearly, some of these methane gases don't just come from cows or agriculture, they also come from oil and gas developments. So we need to think carefully about how to implement that as well. It's not just technology for its own sake. Another example from the Satellite Applications Catapult, we've been looking at plastics in the oceans. How can we observe plastics in the oceans which are not only dirty but also not good for our planet if they build up, affecting fish and all sorts of other things. If we could detect that with more precision, that would be even better. And we can see quantum technologies helping with better sensing, better positioning, but also better computing along the way. So the initial work is sensing improvement, but followed by better positioning downstream.
Wonderful. And Sonali, if I can turn to you, could you give us a little bit more insight into the use cases and also here in the UK, what we're seeing?
Yeah, I think perhaps also just worth mentioning my journey into quantum computing. So after my background in academia, I was fortunate enough to do an Impact Acceleration Award as a postdoctoral industrial fellow looking across the quantum technologies plethora of how we can onboard early stage quantum tech into space. And I spent 5 years working in the Scottish space sector and led some of the first quantum key distribution satellite technical lead of 2 of them, one of which is flying on KeySat next year from Canada. And at the same time, we were looking at Earth observation use cases from space, for example. So very much had that end user perspective when I was there in industry. Now at the moment in National Quantum Computing Center, I lead our innovation strategy for the end user framework. How do we engage with the end user to identify use cases all the way through from awareness to advocacy? And identification of use cases which are relevant to society is one of the pillars that we look at very carefully. From a UK national strategy perspective, responsible research and innovation is something that's really important and something that we want to engage with and have started engaging with quite early within the NQCC. So we have a full-time officer dedicated to the role of responsible research and innovation. We have already had a roundtable with industry players, getting them involved with very early stage within the policy and regulation landscape, making sure that we're not, or at least trying to minimize, we're trying to make sure we're getting people involved in the discussion early enough. I'm sure we'll make mistakes along the way, but we can all try together to minimize that in a responsible manner. Going to use cases, it's been really interesting to see the plethora of use cases that's been coming to us through the Innovate UK and STFC calls that we fund. Some of the interesting ones within the topic that we are discussing have been within the aviation sector. Some of them have been increasing fuel efficiency through increasing the loading of containers on an aircraft. Another one has been optimization of flight paths and how we can use that to increase fuel efficiency and reduce the amount of fuel usage in the aviation sector. We've also funded quite a few projects into drug discovery and chemical design, basically molecular design, as my fellow panelists were talking about. It's been really interesting to see how people have been working across their AI data pipeline, for example, which they have been using to simulate molecules. As Carmen mentioned, if we have more than 50, 60 molecules, then current HPC clusters cannot simulate them. So if we are looking at how to generate, better ammonia, how to generate better green hydrogen, if you're looking at better fuel cells and batteries, these are problems that we will need to look at within that chemical sector domain, which is one of the early movers. And we are hoping that, actually it's predicted that this is the sector that's going to show some of the first advantages of quantum computing. So one of the examples that we saw that within this data pipeline, there is one particular step which is the actual finding that lower energy state, but I don't want to go into jargon, but basically there is one particular state within that data pipeline which you can take to a quantum computer, because that is the state where you're actually simulating the quantum properties of the molecule on a system. So you don't have to replicate that entire pipeline. We can break it down and we can take that one particular step, outsource that to a QPU, find the results, bring that back into the AI pipeline and see whether that's more efficient to do that. And they have been, the first 3 months long project that we funded actually showed very encouraging results, and this is now converted into a longer Innovate UK call. So we are hoping to see this, we're really waiting to see the results of that. But I think the really interesting thing is that all of these projects actually have algorithms or actually have everything they're exploring are translatable to various different sectors. So if you're looking at one particular data pipeline and drug discovery, then this is the exact same thing we can again apply to different chemical processes and how do we make efficient fuel, for example. We're also liaising quite closely with the Office of Quantum and DCIT, and through them with the various different sectors. Energy sector is something that we're closely liaising with, and the transport sector as well within the government. We've got really good responses. There's good appetite for investing into quantum computing solutions and seeing that we are going towards meeting our net zero goals. So very much in support of that, and we are doing as much as possible, but we're always looking to engage with end users as much as possible so that we can drive solutions through that lens.
Wow, okay, so we've heard about a wide range there of exciting applications in quantum as a force for good. I'd like to dig in now a little bit more on the kind of the realities of bringing this to life, and Carmen, I might come back to you first in terms of actually the work that New Quantum is doing, and how can that actually help to bring these sorts of applications forward?
Sure. So what we're working on is essentially the scaling challenge of quantum computers. So we're building computers with qubits, which are very, very sensitive, error-prone quantum objects, and they're very hard to assemble and control with high fidelity. So they make mistakes. So what that means is that we need many of them to encode single entities that don't make mistakes, where we can do actual quantum logic. So what that means essentially is that we might need millions of qubits to tackle some of these very large but very, very critical applications. Now, qubit technologies have made huge progress over the past decade and more, but we know that we don't know how to assemble and control millions of qubits in a single machine, in a single core. We already know those limits, and we know they are coming in a few years, in 3 to 4 years. So really to bridge the gap to where we think we can get to with qubit technology in a single core, which is maybe thousands, tens of thousands of qubits to millions of qubits, the only way to do it is to do what classical computing did, which is to assemble and interconnect many machines together in a farm, in a data center, so that they can work as a larger distributed machine. That networking layer is what we are building at New Quantum. It's a big challenge, so it's the technology around the world, even in academia, is at a very early stage. But that's the kind of infrastructure that we think we need to accelerate, to reach the scale, to accelerate progress. So once we already have quantum computers. What would happen if there were two paths to scale? One is to continue the R&D to increase the number of qubits, and another perpendicular one is to interconnect them. Then, that opens up another path to scale. And then the other thing that I think is important in the context of the conversation around net zero is modularity. So and this comes back to what you were saying, ideally we want to avoid making one huge, inefficient, CERN-type machine, right? That will consume a lot of power. If we can design the infrastructure properly in a modular way, then that will allow perhaps more efficient solutions and better system architecting of the full machine, and potentially be a bit more cognizant about things like energy consumption and efficiencies.
Great. Okay, and then perhaps to Mike and to Matt and to Sonali, I could ask you for your views on, so how much of this is sort of, separate the hype from the reality, and also, we have the urgency of the climate crisis and some of the other problems that we face. What of the impacts and applications we're talking about? What might we see in the next few years, and what is kind of versus what is 2035 or beyond?
Well, let me go to the short term first, if I may, and maybe others can add. It seems to me that for the climate crisis, we need evidence. So a lot of the sensing we do to do with weather, climate change, a lot of that actually comes from space. A lot of it comes from sensing. It also requires data analytics, and that's only going to increase as we get more and more data. It's only going to require more precision to know where the climate change is making the worst impact or the best impact. So more precision. And all of these come with more advanced techniques, such as quantum. I put these in the category of quantum technologies first, deliberately, because actually the sensing journey has already started. The instrumentation journey has already started. Some of the quantum computing may take a bit longer. If I take an example from the sector I know best, which is mobile, we've certainly, as a mobile industry, looked at UN Sustainable Development Goals, all of them, for the last 8 years, and reported on progress in that area. That is something we can build on and say, how can mobile embrace quantum in the Sustainable Development Goals area? We've got mechanisms and processes, but it doesn't all require everything to be developed with quantum in mind first. Some of the examples that Luke Ibbotson referred to earlier on talked about quantum key distribution. That's less of having an impact on the planet, but more having an impact on security and making sure privacy is maintained. So I think we need to broaden the definitions of how these technologies can improve all of our planet, and perhaps broaden the question about quantum for good for everybody, the sectors that we're serving as well as the public. The sectors will benefit in different ways. So health, transport, financial services, space, they'll benefit in different ways, but there's lots we can do.
But on the space sort of applications you were describing, when do you think we will see meaningful improvements in our capabilities that will be applicable to the environmental challenge?
Quantum's being designed into space instrumentation now, and therefore some of the techniques for better sensitivity will come through in the coming years. As Sonali said, you know, she's on a spaceship coming up soon.
Okay, and Matt, perhaps you could, you were talking about some of the sort of chemistry applications.
Well, it's not so much chemistry applications. I guess the question really is how do we get there? And I like the point of, in order to understand anything, you've got to measure it first, and then you've got to do the analysis part of it. So let's assume that there are very clever chemists, and let's assume that there are very clever quantum physicists that can actually make that come to pass. To the point that was being made on modular design and understanding how we actually make the journey, we're working with partners at the moment who are doing two sort of slightly parallel journeys in their development of quantum computing. There are those that are looking absolutely to do the scaling problem, to put as many qubits as they can together, understand whether they can solve the error correction problem, and actually make progress. There are those that are focused on quality, like OQC in the UK, who believe that actually if you get the quality up, then actually when you come to scale, you've already solved a lot of the problems along the way and therefore put in place a building block to do that. And then there's the interconnectors like Carmen, who basically are ultimately going to be joining all the blocks together to try and paint simple pictures, because I like simple pictures and I like working them through with the team. Years ago, when I joined the semiconductor industry, there was a thing called a roadmap, and it was known as the ITRS roadmap. And basically, it was a very, very simple thing in the fact that it was a wall with lots of colored blocks in it. And if we had a technology solution, we colored it green. If we had the development of a solution, we colored it amber. And if we didn't know how we were going to solve the problem, we colored it red. In terms of talking to the market today, in terms of talking to each other today, and coloring in all those blocks on the quantum journey, do we actually understand which blocks are solved, and therefore which we have technology solutions for, and then potentially which ones will have applications that can map onto those things that we've already solved, so we make the right decisions on our journey early and recognize which things are going to be solved later? I think the answer is lots of people think they know lots of things, but I don't think collectively we've actually sat down and done that piece of work. So then when it comes down to the efficient development of those blocks and recognizing where we're going to put our efforts to make the gain, either move a sensing problem or a chemistry problem or a straightforward analysis problem of multiple data sets through, do we know what the bits of the solution are and the stages and the year that we might get there? And trying to put a year around anything in quantum is tricky at the moment. But ultimately, there's various different partners that are going through that journey in different ways. And ultimately, What we don't yet know is actually which of the technologies that are being put out there by the different partners are good or bad or indifferent. And it's probably worth, at some point, talking about the legislation and the support that various organizations in the world are doing to try and help that roadmap and help that journey be understood.
Yeah, I'd like to come back to that thread actually, but Sonali, back to just your sense of what we might expect when.
Yeah, I think similar. I think agreed with all the points that were said by the panelists. I think sensing is already there, and we have instruments in space, and you're finding out analytics, and you're seeing exactly. We're measuring more precisely what's going wrong in the atmosphere, and you're capturing data through imaging and various other technology that we already have. In terms of computing, obviously modularity, there's so many different parts of that puzzle. We have to wait till fault-tolerant computers are there, obviously, to solve large-scale problems. But in the meantime, there's a lot of things to get ready, a lot of parts of that puzzle to keep pushing forward, because quantum readiness is a long-term journey, and we can't suddenly get there if we are waiting just for the commercially relevant computers to be on the market. So we have to keep investing, but it's also at the same time very important to, through our funded projects, figure out these problems are actually not relevant for quantum computing, which is something that the Quantum Computing Center is also trying to do through our funded projects. And the faster we do that, the better, because we can then focus our energy on the problems that are actually relevant. The other thing is about whether we are at a level where we can talk about what materials we're using for building hardware, whether we can do that in a more responsible manner and so on. I think, again, the end user community as well as the hardware community probably has to have they have to come to a point where that becomes a discussion. There probably is going to a point where that starts becoming a discussion, and discussions about modularity are very important to that side of things. And then there's a discussion about whether quantum computers can be much more efficient than current data centers and HPC clusters. And again, that's the journey that we have to take. We obviously have that immense potential and the promise of it. But what does the journey look like? Whether it's messy, whether we're going to make more mistakes along the way, I think we have to tread it carefully and bring people into that discussion, think about it in a much more, we have to risk assess every time that we move forward here, I think. Yeah, so agreed.
And one other thing I just wanted to ask about while we're on the kind of the practicalities. I mean, as a layperson, I had it in mind that that classical computing, it's an enormous energy consumer. I don't know what proportion of global energy gets consumed by it, but I imagine it must be chunky. I mean, I guess like maybe between 5 and 10% of global energy or something. It must be a lot. Does quantum computing have the potential to address some of that and reduce energy demand? Obviously, it's got its own different energy demands. Or is that a bit of a red herring? I wondered, Carmen, you're probably looking at this a bit hands-on. I think, Matt, you might have some views as well.
If I may, before I answer on that point, just wanted to pick up on something that Sonali said, and also something that was said in the previous panels about being ready, about only luck happens when you're ready for it. And I think this is something that should be really present in some of these use cases. So we've spoken in a relatively simplistic way about this chemistry use case for net zero. If someone gave us a fault-tolerant quantum computer today, we wouldn't know how to run it to solve those use cases. So there's a whole industry moving forward, being built to that moment, and there's already companies thinking about what exactly are those problems? How do you tackle them in a quantum computer, but in a way that is directly relevant? And just wanted to mention that even though a lot of what we've spoken about now is the long term, there's many companies already working on kind of climate change related problems today. So like our friends at Multiverse here today and OQC, who have, so I was speaking to the Multiverse team earlier, they work with a lot of energy end users, and work on problems from optimization of processes to prediction of where energy demands will be, etc. So this is all part of the industry getting ready. To your point about the question around energy consumption, I'm afraid I think we don't really have the answer for that. So I would love to say we will definitely reduce energy consumption. I don't know that we have an answer to that, in my opinion, yet. So.
To put a few numbers around it, perhaps then, if I take the scenario of a current superconducting quantum computer being put in a data center, today to run that quantum computer, and I don't just mean the instrument and the qubits and the cold space that's required, but all the instruments that are around it to control, measure, and read out those qubits, might cost you 20 to 40 kilowatts worth of energy. In the context of the energy being used by the data center, that's insignificant. But there again, there's maybe only a few tens, 100 qubits in that system. To go to effectively a million qubit system, which is what people are talking about to start really analyzing big chemistry data sets, well, you multiply that up, and actually the amount of energy that's required to actually run a million qubit system starts to look about the same size and the same scale, or maybe a little bit more than the current data center. But I think you've got to come back to the point of what's it giving you? The answer is you can't solve the problem before, and therefore the outcomes are never in your favor. Whereas if you've got it, the fact that it actually consumes, perhaps even if it consumes more energy, but actually allows you to solve a bigger problem and make a gain elsewhere, well, does that actually matter? And I think there's always this great challenge of everything must always be better than the thing that came before for it to be relevant. But is that the right question?
Okay, thank you. I think red herring is the answer then. So, I wanted to move on to. I mean, Sonali, you touched on policy earlier, and I think it's a very interesting set of questions around to what sort of policy framework should we have around this? I mean, I know in general we tend to like to let the entrepreneurial and sort of academic drive take it where it will, and the market will follow, and the use cases will speak for themselves. But as we've seen recently with AI, actually perhaps to have a policy framework in mind would be a helpful thing. And I'd very much like your views on what are the key components. But also, I mean, Matt, I heard you talking about coordinating, and Carmen, you were just talking about being ready. So again, perhaps there's a role for policy there. And of course, I mean, Mike, you have huge experience in government, which may have a bearing on this. But perhaps I get each of your views, but Sonali, starting with you, if I may.
Yeah, I think like Carmen just raised, so the UK has the ambition of being the first ever quantum-ready economy. And I think this is a great ambition. But basically, like that roadmap of getting to be quantum-ready has all these different aspects to it. So, and policy and regulation are a big pillar of it. So within our flagship Spark program, which is the NQCC's user engagement program. So we have the skills and training pillar, which is looking at how do we develop all of these skills around both technical quantum computing skills, but also hardware skills, software skills, business development skills, policy and regulation skills all throughout the stack as well as outside of the stack that you would need to support the entire ecosystem. And then you have the the application development side of things and the hardware development side of things. And the other side is the policy and regulation. So over the last 2 years, we have been very closely engaging with the various various regulators. In particular, we have had a long stream of work with the DRCF in the UK and their member regulatory bodies. And we are in the process of scoping out a regulatory framework. How does that look like for quantum? We have been following the public discourse on AI. It's really, really important to make sure that we actually have an opportunity here where we can actually start building in those regulation and policy from a very early stage. I think technically speaking, when we are talking about technical regulation, a lot of these regulatory frameworks will be sector-specific and application-specific, so we might not have to really reinvent the wheel here. But we have to, basically, the NQCC here wants to play the role of the convener, where it brings in the regulators and allows them access to seeing how the process of innovation across the quantum computing use cases or hardware development actually works, allow them that visibility throughout the process. And then that allows them to develop that understanding and that knowledge exchange, both within the NQCC or within the end user community of how does the regulation community work, and within the regulators of how do the quantum community work. So that's one. The second is outside of technical regulation, then you have all of these other regulatory concerns like market dynamics and competition and export, import, and all of that, which people are already starting to engage with. And then there's ethics and responsible research and innovation, which I think everyone's engaging with already, because if you want to combine quantum computing and AI in the future, then it's going to be a hell of a lot to deal with for the regulators. So I think the regulators are already primed. They already had 12 months long programs of, they've had quite in-depth programs of looking at quantum computing. Each of them have their insights team, and they have been working with the quantum hubs as well as the National Quantum Computing Center for knowledge exchange. But I think at this point then, we are looking at what is the right moment and what is the right mechanism for engaging further and deeper. Because again, this has to be really informed and nuanced and at the right time. And I could point you towards, there's an international regulatory roundtable but coming up in November, but that's more on the security side of things. But again, regulators are kind of on the ball there, and hopefully that will be replicated across the quantum technologies.
Thank you. Carmen, what role would you see for regulation here?
I think there's a huge role. I mean, I'm just thinking about an example we have today of what happens if when you don't have regulation in tech. So probably many people here heard, but one of France's biggest AI startups, Mistral, launched their large language model, I think last week. And very quickly, people realized that it didn't have moderation. And in fact, you can ask it how to make a bomb, how to self-harm and harm others, and it will give you very detailed step-by-step instructions of how to do that. So this is a startup that raised 100 million euros in week 2 of existing and launched their model in week 4 with no moderation, and of course there's not enough policy and regulation. So I mean, I think it's just worth, because sometimes we don't, we have some examples of what happens if we don't have the right policy, but they seem far away, they seem a stretch. Whereas this is very relatable, right? This is a startup that startups in quantum computing could relate to. So I think the work being done by the NQCC and others, and also the World Economic Forum is really, really crucial for quantum computing, and hopefully we're still in time to put some sensible policy in place.
Yeah, thank you. And I know World Economic Forum is very interested in those topics and supportive of that. So Matt, your views on this?
So sometimes when people start talking about regulation, there's always that concern that means constraint to innovation. And actually, I don't always agree that that's true. I think sometimes if you understand the framework very early on and you understand where you need to be by the end, actually, you will work your way to the right point in time. And I think sometimes getting the regulations and the legislation in early, and whether that's part of the assurance process that says actually we'll only release a thing when we've gone through a certain assurance step, or whether that's an environmental consideration that says actually the thing that comes next must be better than the thing that came before, or whether that's a pollution or a sustaining, whatever those things are, I think if you get the framework in early, you actually end up doing a better job, and I think that's my key point. And there's plenty of people, whether that's NPL, NIST, MITRE in the US, Japanese organizations, that are already doing a lot of really good work here, and I know our NQCC is involved. Actually, I can't wait to see what comes out of this. I think it's really important.
Yeah, so you're talking partly about setting parameters, but perhaps even earlier on, I think you talked about coordination as well, coordination of the components.
Oh, completely. And I think there's a regulation and legislation can help with that, but it doesn't necessarily mean that it will. And I think in one of the discussions we've been having, there's been this topic of sustainability. And people assume that sustainability always means the environment and the planet. But what if sustainability meant the ecosystem that's quantum development? In that there's an awful lot of things that are getting proposed and companies that are going out for funding. And actually some of the things they're asking for or some of the things they're claiming are quite spectacular. Let's use the term spectacular. And actually having organizations like NPL, NIST and others that actually sit there and go, well, actually, those are not necessarily problems that need to be solved, or actually, even if they were, that's perhaps not the best solution in the world, as independent arbiters might actually make sure that some of the right investment is funneled in a sustainable way to the things that are most important. And that would certainly be something that I would welcome.
And Mike, I think it was Ronald Reagan who said the scariest words in English were, "We're the government, we're here to help." But how will the government really help?
Well, first of all, I sat on the National Quantum Technology Programme for 4 years and looked after some of the international relations within that. Quite simply, having a framework, such as a National Quantum Technology Programme, shows there is a research policy and has been for some time. What may now be needed is an applied research policy, which looks at certain sectors in more detail. How will quantum fit space, telecoms, health, more directly, even climate change more directly? And I think that ownership with industry has to be bridged more fully beyond the research community. Applied research needs to have sector knowledge and sector champions. I'd also add that I think a key aspect of quantum is that it's been chosen by the government as being one of the leading 5 technologies. Rishi Sunak was very keen to make sure there was some prioritization. So quantum, AI, engineering biology, semiconductors, future comms, that's setting priorities because there's not enough money to do absolutely everything in science and tech. Working with them together is also a good idea, rather than treating AI and quantum in isolation or even forgetting occasionally photonics. You know, we need to link them together. And lastly, I think the international policy in this area needs some work. Who, to be very clear, are we going to work with? When, how, and when? Who is the opposite number to deal with when it's UK plus X? These things are needed to be understood by the investor community, by the climate change community, but also those who are concerned with security. Export controls comes into this area, so we need to treat this issue very seriously from an internationalization point of view. I'm pleased DCIT have chosen to set up a new office for quantum, quite simply because it will deal with some of these policy issues. And then if regulation is needed, then they'll bring in the regulation to protect the public or even industry from the worst efforts of itself.
Thank you. I think a persuasive case from all of our panelists there for the need for a strong regulatory and appropriate regulatory framework. We're almost out of time. But I have one last question I'd like to ask each of you, which is, what excites you most about the potential applications of quantum for good? Again, perhaps Sonali, do you want to start and we'll work our way down?
Yeah, well, I think we are at a very, well, interesting might be a very, I don't know, like, we're at an interesting point in humanity's lifetime on this universe, and we have lots of problems to solve. So I think I'm really hopeful that with the plethora of new technologies, cutting-edge technologies that we have upcoming, that in case we manage to hit the right timeline and connect them all together in the right way, we'll be able to solve some of these biggest problems. And climate is definitely one of those to tackle. So that's what excites me, but also terrifies me at the same time.
Yeah, I think to me is that we are able to crack this problem fast enough to really, really make a difference in the fight for climate change. So we hear a lot about the quantum space race. So that's more about national security and each nation state building up their capability, which is critical importance. But maybe we could also talk about the quantum climate race, which is, coming together to really, really, really contribute to climate. And that's something where we do need speed.
For me, it's 2 simple words: speed and efficiency. This is perhaps one of the best tools that we've had the potential to have for a long, long time. There are so many different ways you can look at it, whether it's computing, sensing, or anything. They're all tools. I love working with teams and people to have better tools to do a better job. The organisation I work for and with absolutely love efficiency. It's what we care about. These are great, great opportunities.
Jobs, productivity, investment, but most of all, collaboration, multi-sector.
Wonderful. Okay, well, look, on that note, we'll wrap up this panel. Please express your thanks to our wonderful panelists.